So we're going to continue part 2 of section 3.1 off of your handouts. This is, I think, on the bottom of page 3 for the examples from the book dealing with, again, just basic limits. Reminder, this means what is happening from the left and right have to match as it approaches the value, not what it is at the value. So let's look at number 2 from the textbook. If the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right, it doesn't matter what it is equal to at the value. We really can ignore this when we're just talking about limits. So we look for this value, which means my answer is -1. Looking at number 4, the limit of f of x is equal to -infinity as I approach from the left and from the right. So therefore, it does exist because it matches. Again, remember, we're wanting the y value to approach the same value from the left and the right. Looking at number 6, we're now looking at a graph. The A is asking for the limit as x approaches 2. So again, I'm going to use arrows here. So as I'm approaching 2 from the from the left, and 2 from the right, so they are both approaching 4. And then for B, I'm looking at -1. So here, and this is actually continuous. So since it's continuous, we're actually good because it actually equals that value as well there. So it's A. I probably put that kind of in the wrong spot there. It's supposed to be up there. Sorry, guys. So the limit as x approaches -1 of f of x is equal to 4. Looking at the next one again, this will, I kind of cut and paste this so you could actually see how the instructions would look. This one says use the graph to determine first the limit as it approaches from the left, second as it approaches from the right, third do they match, which means the limit exists, and 4 what is the actual value at that. So I'm going to actually kind of draw out a chart just to make this a little bit easier to answer. So the first one we're doing the limit as x approaches A from the left. Then we're going to do the limit as x approaches A from the right. Shrink this down a little bit. Then we're going to do the limit as x approaches A. And finally, we're going to say what is actually the value at that spot. So we're going to start off with a equals 1. So a equals 1 is here. So as we approach from the left, you can see here as I'm taking my cursor across, we are approaching a y value of 1. As I'm approaching 1 from the right, I am also approaching 1. Since they match, my limit exists. The actual value when x is equal to 1 is this dot here that represents the point 1, 2. Looking at when A is 2, which is over here, as I approach it from the left, it's approaching the axis, which is a y value of 0. As I approach it from the right, I'm also approaching the axis. They match, and this is actually a continuous graph, which we'll be talking about in later sections. So the value there is 0. 20 is looking at one where the problem is actually asking you to fill in the table. You can really pretty easily put this into your calculator, type it into the y equals, and then go to the table function, and you can easily do this piece. This is what I talked to you about before. This actually has a graph. Remember, this would have an asymptote at x equals 3 because the denominator can't equal 3. And so we would actually have a graph, something like this. This is just a rough sketch. So you're literally just taking this and plugging it into your calculator and getting your answers. So 12.971 here would be 127.08, 1,268.2. Then we're skipping down to 1,268, 126.5, negative 12.39. You can use the graph, but I think the tables are easier to use on this case because it's asking for it. I think when you are looking at some of these problems, you're going to find one way is easier than the other, and you kind of have to make sure you're following what the directions ask, but always look to see, you know, if you can check yourself using a different format. So now we're going to go to our rules. So there's a lot of rules on this piece here, and you want to kind of be able to refer back to it, but this is what we're going to use for algebraically solving. If you think about it, some of these again are common sense, but it's just we tend to overanalyze them. So number one says if we have a constant function, think about that. That would be our horizontal line. It doesn't matter what I'm approaching, I would be approaching that actual value. So that's what we're talking about for the beginning of that piece. If we have a function, we can break it up and look at the function separately. Denominator, numerator, okay, adding, subtracting. A really important one you're going to use a lot is if we have a polynomial. Polynomial, if you stop and think about it, it has no holes in the graph, it has no jumps in the graph. You could actually trace it with your pencil. So we don't have to look at the graph here. We can literally just plug in the value because that's what we would be approaching from both sides. So we could take the x equals a and plug it in. So we're going to look at some examples here. So you're going to want to have your paper out so you can also look at those pieces here. So just kind of put it in a chart to quickly go over some ideas. So this first one just kind of goes over the idea. Again, if we're talking about a constant function, if my function is always -6, it doesn't matter what I'm approaching from left to right, it's always going to be -6. If I have a continuous graph, which on the right hand side, 4x cubed minus 7x plus 2 is a polynomial, it's actually a trinomial here that we're dealing with. So there will be, again, no holes in the graph. So in this, make sure you're careful with your signs when you're plugging it in. So we end up with a -4 plus 7 plus 2, which ends up giving us 3 plus 2 equals 5. So number 1 and 2 I can plug in direct. Number 3 we want to run into the problem because if I plug it in to the denominator, I get a 0. So if I have a form when I'm plugging in, I get 0 over 0. Basically what it's telling you is that you need to factor it out. There actually is a hole in the graph, so it doesn't exist at that value, but the hole is going to still make it approach that. So when you plug it in, if you didn't catch it, if you get 0 over 0, it means stop, go back, and simplify by factoring. So right now, just for space, I'm going to put an L with a circle to say that I'm doing the limit. The top factors to x plus 5, x minus 1, bottom x minus 1, x plus 1. So the x minus 1's cancel. Now I can plug in that value of 1. There is a hole at that 1, okay, but I'm okay now because we know we will approach it from both sides. So I will get 6 over 2, which is equal to 3. This second one's a little bit more complicated in your heads because y'all don't think of being able to factor this. But I can't plug in 36, and if I plug in 36, I'm going to get 0 over 0, which tells you should factor. So we normally are used to factoring if I have x squared minus 36. I don't this time, but on the top you notice I have a square root of x. So that should lead you in the direction that we're going to factor. This isn't our normal piece, but x square root of x minus 6, square root of x plus 6 would still be a difference of squares, which would give me that value. So now these cancel. Be careful, remember there's a 1 left on the top. And now I can go back and plug in the 36. So I end up with square root of 36, which is 6 plus 6, which is 1 over 12. Try to plug it in first. If you can't, 0 over 0 tells you can factor it. Going to number 4, we get a 0 on the bottom, but a number on the top. This would be where I actually have a rational graph that has asymptotes in it. So if you're ever confused with these, I actually suggest to graph it. But if I were to plug it in, I would actually get a negative 12 over 0. So I would suggest to graph it in your calculator, because that clarifies to you if the arrows are going both in the same direction. Remember, on the asymptote, if it's going both up, both down, then we're going to include negative infinity, infinity. If they're going opposite spots, one's going up and one's going down, which is this case, it does not exist. For number 5, you will for sure have a problem on this test that you will have to graph with piecewise and then answer questions from 3.1 and 3.2 onto the graph. I suggest doing this problem in a format. So I'm going to break it up, and I'm going to do the first piece, which is f of x is equal to negative 1 when x is less than 2. Okay, so we're going to do points x and y. So in this case, for x is less than 2, you always have to do the boundary, and then if there's an equal to, it's closed. In this case, it's just less than, so I've got to put the 2 in. It's negative 1. Less than 2 means, all right, let's plug in a 1. It doesn't matter what I'm plugging in. It's a constant. Okay. But I'm going to go ahead and plot that. So I have the point 2, negative 1. Be careful, it's open, and then it's staying constant all for every value x is less than 2. So that's my first piece. Going to my second piece, my function is equal to x minus 2 including 2 up to 5. So this is a linear line. So we should know what the graph looks like, but we always need to do our boundaries. When we plug in 2, we get 2 minus 2, which is 0. This is closed because there's an equal to sign on it. If I plug in 3, I get the point 3.1, and I need to at least graph the boundaries. This one is open because there's not an equal to on the 5. 5 minus 2 is 3. So I start at 0, 2, 0, 3, 1, and then 5, 3 is open. That's my second piece. Third piece is f of x is equal to 3 when x is greater than or equal to 5. So start at 5, and that's closed because there's an equal to sign on it. And this will always stay constant in this case. So at 5, let me make sure I mark that mark. In this case, even though I had an open for the green, I now fill it in. So even though one of them was open, it's still colored because the other one overlapped. This is my drawing, and now I'm going to use this drawing to answer my questions. So this first one, limit as x approaches 2. So as x approaches 2, from the left side, I'm approaching a value of what? I'm approaching that value, and it should be on the tick mark. Again, my tick mark's a little off. It should be approaching negative 1. From the right side, I'm approaching 0. So doesn't exist because they don't match. Approaching 5, even though the green had an open, it's still approaching the same value from both sides. It doesn't have to be a smooth piece. They're both approaching 3, left and right. And at 0, which is here still on the blue, we're approaching a negative 1 from both sides. Practice drawing these pictures.